Hi, this is from 5.1. We're talking about summation. It's also meant to be connected to the conversation around Riemann approximation methods. Okay, and so in that conversation, we have to figure out what is the way to represent the area under the curve. And I want to try to paint a picture for you and push, maybe in this video, maybe in multiple parts, how to go from this symbol and just what it means to be a sum of numbers, to the idea of how it helps us calculate the area under the curve. In that previous video, watch parts 1 and 2, it kind of talks about some information you can do with that. The goal of what I want to get to is this idea. The limit as n goes to infinity, where n is the number of subintervals. And then we have this connection of some boundary points, like the boundary of the interval, and then this function. How do we define the function so we know exactly how to set it up? Let me talk about the function we were using originally. The original function was x squared. Here's our function. We want to talk about the area under the curve. So just a little backspace to move forward. If this function looks like this, and we're bounding it from, 0 to 3, I think has been the consistent result. So here, what we mean by the area under the curve is everything from 0 to this value. That's not actually that much of a stretch in logic, but what I'm trying to get to showing us is that so far, our notes in class or our conversations have been around this idea of drawing rectangles. But I haven't introduced a formal way to think about things until this video. Our rectangles were like right Riemanns, and so we drew a bunch of rectangles from the right side of the shape. That's an overestimate. Sorry for the bell. This is, of course, during school hours. Okay, so this is an overestimate of the area, and the conversation was, well, as the number of subintervals, like I've got 1, 2, 3, 4, 5, 6, 7 subintervals on my drawing, as I make that number of subintervals increase to infinity, then the number of rectangles that I actually create is going to get, well, it's going to increase, but their base is going to decrease. So I've got a rectangle here and a rectangle here. And in fact, I kind of drew it already just in the way I shaded. Imagine all of those were little rectangle lines. There's a rectangle. And eventually, with a million bajillion, mathematically correct term, by the way, integral or rectangles, we do wind up having the area under the curve. In our summation structure, we're looking for some relationship as n goes from 1 to infinity. We need to start with some amount of space. We want to figure out a way to talk about how many rectangles there are. The structure of the area under the curve is based upon what we already know for the area of a shape. We want to talk about area as base times height. How do we figure out the area of each rectangle as the rectangles grow from being a certain size out to infinity? Let me say that this is the long goal, and I'll give you a part 2 that brings in the formal notation. So we're going to call the rest of what I'm going to tell you right now kind of an introduction that wraps up what we did on the spreadsheet. Let me use our example here, f of x equals x squared. A little redraw. Erase. Okay, this is at 3, so that must be a height of 9. 1, 2, that's at a height of 4, and this one is at a height of 1. Okay, 1, 4, 9 on the heights. This is meant to represent that function. If I draw left, let's do left Riemann approximations. If I draw from the left side of each of these 1, 2, 3 subintervals. Drawing from the left side, I'd have a rectangle with a height of 0, a rectangle with a height of 1, and a rectangle with a height of 4. So the area would be what I get from adding up those 3 rectangles. Okay, let's code that out. So the base of each of these rectangles is the length of the subinterval. To find the length of the subinterval, I take the upper bound and the lower bound subtract them, and then divide by 1, 2, 3, that I've got 3 subintervals, which I'm only choosing 3 because I know I can see a jump by 1. The comment that I've made the last couple of days has been, what if we go by a half? 0 to 1 half, 1 half to 1, 1 to 1 and a half, 1 and a half to 2, etc. Okay? So we need this information. We're going to call this our delta x. But that's also the base of each rectangle. So in the first rectangle, now the next thing that we need to do is we need to add up all of the height. All of the heights would be 0 plus 1 plus 4. So in order for us to add up all of the heights, we have to bring in the conversation with the actual function itself. This height right here, I hope the green is coming through. This height right here is 4, but it's also, in terms of our function notation, it's 2 squared. Over here, this height, 1 squared, and not really all that surprising, but 0 squared. Because of the way this is designed, we can now think about the heights of 1, 2, 3 rectangles being added together. That was the comment I've also made in class before, but I want to push to some notation. So in this problem, the notation is going to be 0 squared plus 1 squared plus 2 squared. Do you see the 0, the 1, and the 2? That starts to look an awful lot like n in summation notation. If you're going to add up multiple things, well, instead of being worried, this is a small list, I know, this is a small series, but let's say that n is really approaching infinity, so we're getting ginormous, extremely long strings of numbers that are added together, and there are shortcuts that we can use. There is a formula to evaluate this. It's in our textbook. So in order to set this up in a way that's faster, let's just use the summation sign. We're going to find the sum of all of our heights. Let's find the summation sign for n squared. As, well, I use n instead of x. That's really just we use I instead of n. There's really just no real reason for us to be picky in this comment. Let's say we're going to go from I, from 0 to 2. That 0 to 2 is the left numbers of all of our rectangles. So 0 to 2 represents 1, 2, 3. Ooh, that doesn't really, that works. This totally works. But let's see if we can stretch this to something a little bit longer. Let's see if we can stretch it to like halves. Maybe that's actually for the next video. Let me finish off this part right here, trying to get the idea of the summation notation, why it's a part of our work at all. To find our approximate area under the curve, our left Riemann approximate area under the curve, given the information that we have, the area under the curve would be base times height of whatever rectangles there are with the curve. So I'm going to use this notation, the sum from I equals 0 to 2 of I squared. That's adding up all of our heights. Height plus height plus height. Fortunately for us, we have all the same base and base and base. That is delta x. So in this problem, I'm going to put times 1. Doing this, right? I want to get the idea of base. No. I pointed to the wrong thing and started writing a different number. This is still using the structure of base times height. There's our height, there's our base, we multiply them together. Thank you for watching part 1 of, 2, 3, a million parts. Let's see as n goes to infinity. We'll catch you on the next video. Bye.